Okay, so it's time to solve an AP Physics free response question. Let's go. Okay, here is our setup. There is a mass attached to a string. The string is 1 meter long. Length string equals 1 meter. And it is attached to a ceiling that is 1.25 meters above the ground. So height ceiling equals okay. It is also given that the mass, this ball here, the mass, um, is equal to has a mass of 1.72 kilograms. Okay, so the mass initially starts at rest. At rest, pulled up here at it, and this angle between the vertical and where the mass is where the mass starts, otherwise known as theta 1, is equal to 31.6 degrees. The mass is let go. It's allowed to swing, and then here it's cut. At which point it becomes a projectile, and it is launched for its the ground. Now, the angle here, where it is cut, the angle between the vertical and the string is 14.8 degrees. And we are asked to find how far, or what is the distance between directly under this, directly under the string and where the mass finally lands. How do we do that? Well, we can split the problem up into two parts. The first part is we have to find out the velocity at this when the string is cut. And once we do that, we can use that velocity to figure out how far it travels. Let's do the velocity when it's cut first. To do that, we have to use a concept called conservation of energy. Now, what is conservation of energy? My handwriting's bad. What is conservation of energy, you may ask? Well, as you can see here, you may or may not know that all energy is conserved. Energy cannot be created or destroyed. There's energy. It's constant. Can't change. The total amount of energy in a system can't change. You can lose some to heat, but that's for later on. For now, just say that the total amount of energy in a system can't change. The trickier part is that there are different types of energy. In this problem, we will only be dealing with two kinds of energy, potential energy, namely gravitational potential energy, and kinetic energy. Start with gravitational potential energy. Now, gravitational potential energy is essentially the energy of an object due to gravity. So if I'm holding this pen up here, it has energy. It's not doing anything, it's not moving, but if I were to let go, it would fall. And it falling would have energy, and the amount of energy it has is based on the mass, the acceleration due to gravity, and how high up I'm holding it, which is why potential energy due to gravity is equal to the mass times the gravity, acceleration due to gravity times the height. Remember that acceleration due to gravity is equal to about 9.8 meters per second squared. The other type of energy that we're dealing with is kinetic energy. Now, kinetic energy is equal to 1/2 mass velocity squared. This is our kinetic energy. And these two, the energies must cancel out in the end. They have to equal each other in the end, because that's what the law of conservation of energy says. So let's set that up. At the beginning, quick sketch. When it's held up like this, we know it's at rest. If it's at rest, it's like me holding this pen up here. It's not moving. Therefore, it only has potential energy, right? So, potential energy. Swing, we let go. Swings, and then, yeah, okay. And then it releases here. Cut the string, it releases. At the point at when we cut the string, or when as soon as we let go, that potential energy starts getting converted into kinetic energy as well, which is why, because it's moving, right? We let go, it's moving. Now it has kinetic energy. We're not just holding it. We dropped it. Yeah. Okay, so now not only do we have the potential energy at this new height here, because here's the floor. So this height's obviously different from this height. It's not, this drawing's not as accurate as my other one. So not only do we have potential energy, but we also have kinetic energy. Now, all we have to do is, the first step is to substitute both of these things in place of this. So we'll do that real quick. mgh1 is equal to mgh2 plus 1/2 mv squared. Okay, there's a few things we can do to this. Well, first off, something you may notice. We have a height 1 and a height 2. That's because these are released at different angles. They're going to have different potential energies. So we have to solve for that. Yeah, so how do we do that? We can use some trigonometry. So let's go to, I'll use this one. So this is theta 1, and that is theta 2. So we know that theta 1 is equal to 31.6 degrees, and theta 2 is equal to 14.8 degrees. Now, if we want to find the height, we know that the total height from the top to the ground is 1.25 meters. Or height ceiling is 1.25 meters. Then, if we find this, here and subtract it from 1.25 meters, it'll give us this here, which is what we want, right? That's how high up it is from the ground. Let's do that. Trigonometry, some little trigonometry here. We can say that the cosine of this angle is equal to adjacent vertical, that's what we want, over hypotenuse. In other words, the height is equal to the length times the cosine of the angle, and it works both ways, right? So now that we have an equation for this height here, we have to take into account that this is only this distance, but we want this one, so we have to subtract from 1.25. So the height, whichever height it is, will be equal to 1.25 minus L cosine theta. Let's plug that in here. So you may notice that our L's are gone, and that is because, per our original explanation of the problem. L is equal to 1. Anything times 1 is 1. Anything times 1 is itself. So, yeah, the L just goes away. You know what else goes away? The masses. There's a mass here, there's a mass here, there's a mass here. Let's just get rid of them. Make it a little bit easier for ourselves down the line. Okay, now we can finally solve for our final velocity. We can finally solve for our final velocity. To do that, we just need a little bit of algebra. So let's do some rearranging here. Multiplied by 2. So square root of 2 2g and we get this very long square root. But when we simplify that down, let's see what I did earlier. When we simplify this down, this will give us, where the hell? Hold on. Okay, sorry, I lost my work, but I did it again. When you input all of the values that we know into this equation and solve for velocity, we will get that the velocity when the string is cut and the projectile begins to, the mass turns into projectile, the initial velocity will be about 1.5 meters per second. Great, that's part 1. Let's move on to part 2. Part 2 is figuring out where it lands. We're lucky. We were given the initial velocity. We just solved for it. It is 1.5 meters per second. But now we have to use something called kinematics to figure out how this object moves. And that's what kinematics is. Kinematics is how objects move. It explains the motion of objects. So there's a lot of equations you can use. Let's see. We have okay. Here are 4 main kinematics equations. We can see that they use mainly they use the variables velocity, initial velocity, this is final velocity, initial velocity, acceleration, and time, and then also displacement, so change in position. So we could try to use these to solve our problem, but that's not going to work because we're dealing with a projectile here. So we have to change it up. Apply these in different ways. Essentially, when you were dealing with a projectile, we have to split our velocity up into components, and we have to split our equations up into components. So we have, like, for example, velocity is probably pointing somewhere like this, but in reality, splitting it up in x and y components, the x is horizontal, the y is vertical. This would give us that our velocity in the x is actually equal to v cosine theta. Our velocity of the y is equal to v sine theta. If you're wondering why, use some trigonomics, and we could see that if this is your velocity vector, this would be the cosine component horizontal. This would be the sine component vertical. Okay, so if we look at these equations, which one are we going to use? That's a good question, and it comes down to a few things. First, one thing is the velocity in the x direction has no, or in the x direction, there is no acceleration. Velocity is constant, there is no acceleration. In the y direction, the only acceleration is due to gravity. Because of this, we want to use acceleration to y when there is acceleration. So we're going to use this equation here. And what we're going to do is we're going to solve for the time in flight. And then we can use that to give us our displacement horizontally, which is what we're looking for. So the displacement in the y and change in y is actually equal to final final minus initial, right? Change is the final minus the initial. So we can rewrite this equation as, so we know that our initial position was the height of the projectile as is cut. And we learned from earlier that the height of the projectile is 1.25 minus cosine theta. And our theta in this case will be that 14.8 that the string is cut from. So the final is, well, the initial is 1.25 minus the cosine theta, but the final, because we want to know when it hits the ground, the final is going to be 0. Setting our reference height to be at the bottom, the ground here. So our final height is going to be 0. So that means our equation is going to look like this. Boom. Now we can substitute in a few things. We know that g, acceleration due to gravity, is equal to 9.8 meters per second. And we know that our velocity in the y is equal to initial velocity times sine theta. Let's do that real quick. It's a little messy, a little craft, but you get the idea, right? So it may not look it, but this is going to come out to be a quadratic. When we solve the quadratic, only one of these answers is going to be positive, and that's obviously got to be our answer. I mean, time can't be negative. So I'm going to run those calculations real quick and get back to you in a second. Okay, so when you run these calculations and you solve for t, you only get one positive answer that makes sense. So your time of flight, or t, is equal to 0.283. Wait, let me check. Yeah, 0.283 seconds. Awesome. Now, how do we use that? It's a good question. We can now go back to our kinematics equations. X does not have an initial, or X has no no acceleration. Acceleration 0. So that means if we use this equation, this term just goes away. A equals 0, and we're just left with change in X is equal to initial velocity times time. So let's write that out. Okay, so let's think about our initial position here. And we're going to go back to our diagram. We're launching from here, but it wants us to find the distance from here, right? So that means if we set this as our 0, whatever we get at the end, we have to add the sine component, sine of theta 2, 14.8 degrees, in order to get the correct displacement. So let's remember that. We're going to sub in Vx for, or we're going to sub in our initial velocity, and we're going to get 1.5. We're going to put our time at 0.283 seconds, and we're going to get an answer. But this answer is not complete without adding on our sine 14.8, because we know we are actually starting from back here. Finally, when you run these calculations out, you get, hold on. So when you run those calculations, we'll break for calculations again. Your final answer will be 0.68 meters.